Welcome to the webinar. Please stand by. The webinar will begin shortly. Please remain on the line. The broadcast is now starting. All attendees are in listen-only mode.
Okay, we are getting started. Good morning or good afternoon, depending on where you happen to be in the world. My name is Eric Culverson, and I'd like to welcome you to a one-day interactive Versal ACAP workshop. So we'll give it maybe just a couple more minutes because people are still finding their way in. But for those of you that are here, again, thank you. Thank you so much for being here. And we had planned on this perhaps being a little bit of a smaller event, and therefore we'd have the opportunity for even more interaction and more questions. And we still want to have as many questions and as much participation as possible. But because we have more people, we have to somewhat limit our way of engaging. Like, we won't be able to just directly talk to each other. So we're going to use the chat feature. So as I go through the presentation, please use the chat to ask your questions. And I will stop every couple of slides, go through every question that I see in the chat, and I will discuss each and everything that you have entered. And sometimes the questions may be a little bit off topic, but I want to try to give you the benefit of as much input and as much feedback as possible. So we'll start with our formal presentation in about 2 minutes. Okay, we're at 3 minutes past the hour, and we are going to get started because we've got a lot of information to go through. In fact, the overall training for the Versal ACAP is up to about 11 days at this point. What I mean by that is that if you take the comprehensive training classes from the AI engines to the broader architecture and design methodology, there's a one-day class that deals specifically with the NOC, and another one-day class that deals with power and board layout issues. So if you took all those together, that would be like 11 days of training. So what we're going to accomplish in this one-day workshop is to highlight some of those really important topics and then end by working through a specific example. And that example is coding a fur filter that uses the AI engines and uses the vector processing capability of the AI engines, which on the surface, that sounds really straightforward. But in fact, it gets a little bit involved because that's a very proprietary architecture, and the syntax that we're going to be using is going to be Xilinx specific. We're going to be using something that they call intrinsics, which are basically C++ functions that Xilinx has written that map directly to this very unique architectural resource. So I want to show you how that's done, at least give you a quick sample of it. And of course, when you're more interested, then please come back for the more formal training. So today, we begin with just an introduction to the Versal ACAP platform. So before we get into that, allow me to fully introduce myself. Again, my name is Eric Culverson, and I'm with Technically Speaking. I've been a Xilinx trainer for approximately 30 years at this point, going back to my days as an application engineer for Avnet, and then started training for the Xilinx tools and technology. I mean, this goes way back, like when there was only the XE2000, the XE3000, and we were really, really excited when the XE4000 family came out. So I've been working with the Xilinx tools and technology for many years at this point. And I can tell you, even though I'm not a Xilinx employee, I'm really excited about this Versal ACAP device. You look at the capabilities, you look at how Xilinx has brought forward everything that was ever good about the FPGA and the embedded processing capability, and they've added to that the AIE engines and the NOC, and they've created something that is really, really special. And hopefully you'll feel that way. Obviously, you're interested enough to be here, so let's get started. The first section, again, is just a quick introduction. We want to talk about, well, what does it mean to have an ACAP device? You know, what's the significance of this? What are these different engines that we're looking at using? And then the different Versal families. So the key concept is a heterogeneous compute platform. Now, this isn't the first time Xilinx has done something in this direction. If you look at the Zinc devices, and particularly if you look at the Zinc MPSoC, MPSoC means multiple processor system on a chip. So this idea of being able to combine embedded processing with programmable logic and platform management, that's really what the MPSoC was about. And of course, you have the RFSoC version of that as well. Well, the ACAP device takes that concept even further. So you still have CPUs. You've also got what would be a GPU capability. And what do we mean by that? So you have independent engines that can work in parallel. So the strength of a GPU is to take computationally intense operations and move them from the traditional CPU into a parallel processing environment. So that's what the standard OpenCL supports. So you can have that same capability here using either the DSP blocks in the fabric or the AI engines. And then you have the traditional FPGA fabric. And even though it's traditional, what we're actually going to see in this workshop is that Xilinx has enhanced it. They've actually made it better. So if you look at any of the previous families, like the 7 series, the Artex, Kintex, Vertex, into the ultra-scale devices, Kintex and Vertex ultra-scale, this particular family's the Versal ACAP, the FPGA fabric, actually is enhanced. So it supports larger designs, supports better routing, less congestion, better performance, and more flexibility for the synthesis tool. The main goal of this is, one, to address future megatrends. And by that, we simply mean that because this is still programmable and it's also going to be software controllable, you're going to be able to upgrade your products and your applications using this same platform and be able to adapt to changing industry standards, different protocols, meanwhile maintaining the same essential architecture. So it's worth learning about this, and it's worth the investment to get trained and educated and to develop some proficiency with this particular platform. This also mitigates the Moore's Law limitation, where we keep just trying to make things faster and faster. In fact, what we really have to do is provide different engines. So that's what Versal ACAP does for us. So the A in ACAP is adaptive because, again, it's still FPGA fabric. You have the ability to update it as necessary, to do a full development cycle, and then create new products or new standards or new protocols or new deployments. Within this architecture, you got the scalar engines, you have the adaptable engines, and the intelligent engines. Now, I'm fairly certain at this point you know what these are. At least you know what they are in general. You know that the scalar engines are like the A72 processors or the R5s. The adaptable engine is the traditional FPGA fabric. And then the intelligent engines are going to be the new AIE engines, as well as the DSP capability. So that's where we're getting our compute acceleration from. So we can look at any system in any application and then decide which of these three processing engines makes the most sense, and then be able to tie that together in a way that creates a highly complex, highly integrated, extremely high performance single chip solution. So this is going to save us power. It's going to save us board space. It's going to give us speed and performance that we just otherwise could not achieve. And of course, it is a platform. In fact, everything begins with the idea of a platform. And what that means, particularly for Xilinx, is you start off with the hardware. Everything that's going to be included, from the different processing engines to the interface to the boot capability, and then you develop applications on top of that. So the idea of having a platform means that once we have defined the platform, we can now do programming, we can add other features and capabilities, and you can do that either directly, or you can use libraries, you can use software stacks that Xilinx has that target the underlying architecture. So there's a lot of flexibility built into this. Now, of course, with that broad capability also comes more complexity. So yeah, this is not the easiest thing to design with, but like anything else, once you learn it, once you make that investment in getting familiar with the design flows and the individual pieces, then you're able to leverage this tremendous capability. So Versal itself is about heterogeneous application and acceleration. So heterogeneous just meaning we've got different processing engines. We've got the A72s, the R5s. We've still got microblades available to us. We've got things that can be done in the fabric. We've got the AI engines, which are themselves like just little RISC processors. So any application and any developer. Now let's think about this for a moment. Any developer. What Xilinx has done with this particular technology and the design flow is they have created a means by which different people can contribute to this. Now, I say different people, meaning from software to hardware designers, people that are well versed in system architecture and using frameworks for machine learning, to traditional hardware VHDL Verilog designers. Now, everyone can contribute, but chances are not any one person is going to do the entire Versal ACAP, because this is a system on a chip. So just like now in your companies, in your organizations, when you're developing a system, you're typically looking at teams of engineers and personnel that are responsible for different sections of that. And then you look at the integration. So you're going to do the same thing here. You're going to have different people contributing to this overall design. And fortunately, Xilinx has thought that out pretty well. They've made the development flow and they've made the tool flow such that it supports this concurrent effort that's necessary. It is truly a divide and conquer approach to excuse me, being able to design these different sections and then integrate everything together. This is built on the 7-nanometer FinFET technology processing for the die, which that also pays dividends for us because that means that it's faster inherently. If you look at the 7 series, that was 28 nanometer. If you look at UltraScale, that was 20. If you look at UltraScale Plus, that was 16 nanometers. Well, this is 7 nanometers. And we know that each time we do a die shrink, we're going to get higher levels of integration and performance. So you have that here as well. This is software programmability and then domain-specific hardware acceleration. So you've got a system here where as it runs, you're going to be able to change parameters using software. So that means you could do partial reconfiguration, and that could be for the programmable logic, but it could also be for the AI engines. And you're choosing one domain over another based on what's best, what gives me the required throughput, operating frequency, latency that my particular application needs and my particular system requires. Because this is so complex and so powerful, Xilinx has actually broken this up into 6 series of devices. That way, you're not buying like one big chip and then you find yourself using only half the capabilities. So you've got different devices that allow you to basically scale what resources you need, utilize combinations of memory, resources, other specific attributes based on your particular design. So the advantages are pretty apparent. You've got software programmability, you're going to have the dynamically adaptable reconfiguration, and then you have the ability to accelerate the application. So from a software standpoint, you can quickly create any optimized solution. And notice they're calling this a software abstracted tool chain. Well, what does that mean? That if you're a software programmer and you want to take advantage of this kind of unique architecture, well, you don't really want to have to understand too much about the architecture. So when you are developing your application, you're writing code, you want that to map to the underlying architecture in a way that's already optimized. So Xilinx is giving you libraries that do that. They're giving you specific compilers depending on which resource you're targeting. That way, you don't have to understand the details of the architecture. You concentrate on your particular application, and then you can measure the performance, and you can evaluate the quality of results by looking at the reports, profiling, looking at the latency, looking at the area utilization, looking at the power utilization, all the things that matter to you. So you're going to be able to program everything in software, and then you can update, and you can do optimal acceleration by moving from the traditional CPU processor into either the fabric or into the AI engines. So you're programming with high-level languages or frameworks and the Xilinx libraries. The great thing about the frameworks is that it allows you to use things like, say, TensorFlow or Caffe on the front end to do machine learning and AI applications, or use the Xilinx libraries, which are already mapped to the underlying architecture. So again, you don't really have to understand that much about the architecture. You just have to understand what functionality you need from the libraries. You're pushing this through the compiler engine, with a pretty standard software development flow. You're compiling, you're using the stacks that are provided, you're using make files, you're doing everything pretty much the same as you would, even though you're targeting a unique hardware architecture. You then run and deploy the resulting binaries, because this is what programs the physical device and then execute the application. Now, of course, that's well, that's a great overview. The development and the profiling and the debugging, yeah, it can be a bit complicated, but it's all there. It's all at your fingertips, and it's just a matter of gaining familiarity with this. So you could dynamically uh, adapt the reconfiguration. So you can do what we used to call partial reconfiguration. Now we call it dynamic function exchange. So you could update things in the programmable logic. You could also update the AI engines, like literally just pass in a different functions. So you're going to be able to add that level of flexibility to an application. And the acceleration itself, well, that's one of the main concepts here, is to take anything that's compute intensive, anything that would just suck up a lot of bandwidth and latency, and instead move it into other aspects of the chip. And what we can do in those other aspects of the chip is that we can unroll loops, we can do pipelining, we can do all different techniques that allow things to run faster in hardware as opposed to a traditional CPU. So it looks like a GPU, but it has more flexibility than a GPU because it's programmed to the specific data type that you're using and the best overall way of manipulating that data. So this is going to give you deterministic performance with the least amount of overall latency. And so the metrics here allow you to do artificial intelligence, smart network cards, high density storage, 5G, ADAS systems, modular radar, just extremely fast optical networks. It's a lot of things that are possible here. This slide is kind of interesting in that it says that the true benefit of the ACAP architecture only comes into focus when you learn how to use everything. And that's true. That is really a fundamentally true statement. This kind of sounds like marketing, but if you think about what the Versal ACAP is capable of, you realize that the whole is greater than the sum of the individual parts. When you really start looking at your system and your application and partitioning it into these different blocks and these different processing engines, you come up with something that is better than just a purely embedded solution, better than just a purely FPGA solution. It's combining all of these that really allows you to have just a tremendous system advantage and still be able to maintain your power limitations, be able to have more flexibility, more system integration, more performance in the same package. So this couple of slides, I should say this one slide, looks at some specific applications from cloud computing to secure networking, 5G, edge deployment. And the great thing about the Xilinx tools is that in each one of these cases, if you go left to right, we're still talking about the same base set of development tools. So we're going to be using Bravado for the initial hardware definition, and then Vitis for all of our software programming and application. And from that, we can then deploy to the cloud. We can deploy for on-premise. We can do applications supporting 5G, and there's actually going to be some specific libraries that support that, as well as ADAS systems. So we can do the certification that's required for that. And they're showing us comparisons between, say, maybe a high-end GPU. So you look at an NVIDIA solution compared to what you could accomplish here using the AI engines. You look at the previous families from Xilinx, the UltraScale FPGA, which is arguably an industry standard right now, but still Versal ACAP is going to exceed that level of performance and integration and capability. Likewise with the RFSoC, there will be a RFSoC version of the Versal platform, which means that we're going to have the direct sampling capabilities. So we'll be able to have high-speed ADCs and DACs and forward error correction built in and around the Versal core. And then you've got ADAS systems, which are going to work much faster in this particular environment as compared to, say, like the MPSoC. So those previous platforms are great, but Versal ACAP is going to be on a whole nother level. And you can migrate your designs from those into here, especially the processor aspect of it, because that's using the same instruction set. So you can actually take an existing system, bring it into Versal ACAP, and start taking advantage of the tremendous powering capabilities. Now, as I said earlier, there are different families. That way, you look at your application, you look at your system requirements, and you can look at this portfolio and say, well, do I need the core series? Do I need the prime series or the premium? So you pretty much get what you need and don't waste money, don't waste resources. The things that are common to all of these platforms, however, are things like the programmable logic. Each one will have this adaptable engine, which is pretty much the what we would call the programmable or the very traditional FPGA fabric. But as I said earlier, even the traditional stuff has been upgraded and it's better. You've got the processing system. So this is the A72s and the R5Fs. Interestingly enough, every device will have those. So that means that even if you don't need it, it's still going to be there. But Xilinx has anticipated that, well, okay, yeah, some customers may have systems where they don't actually need the processor capability. So the boot and the configuration does not require that, which that's different. Because if we think back to like the Zinc 7000 and the Zinc MPSoC, then those processors were directly involved with the boot and configuration mode. Well, in this platform, they don't have to be. They can be, but they don't have to be. We have a separate management resource for that. You've got the hierarchical memory, which starts with the memory that's inside the FPGA fabric itself. The lookup table-based RAM, the block RAM, the ultra RAM. In some devices, you even have something called an accelerator RAM, which is a really large 4 megabyte chunk that's broken up into smaller blocks. And the idea of that, if you're doing something, let's say like an OpenCL type application, where as part of the OpenCL standard, the processor is controlling this hardware acceleration kernel. And as part of that protocol, the processor copies data from the host side memory to the global memory. And the global memory is then able to be seen by both the host as well as the kernel. Well, that's what that accelerator RAM gives you, the ability to copy over a massive amount of data and then have that be directly available to the kernel. And then once the kernel completes processing that particular chunk of data, it writes those results back to global memory, which in this case is the accelerator RAM, and then the processor can access that. You're also going to have serial transceivers. Now, which transceivers you have depends on which device. If you go from the core to the prime to the premium, the data rate of serial transceivers varies. So at an absolute baseline, you've got the 32 gigabit transceivers. So every device has that. And the premium devices, you can get up to a 112 gigabit sample rates. You've got memory controllers. And this could be the traditional DDR4 that's going into the fabric. So this is a soft version, or it could be an actual hardened controller that's built into the so-called CPM module, and also directly supports the high-speed debug port. So depending on which device you have, you'll have different memory controllers available to you. This network on chip, we're going to spend time today talking about that, because that's a key element of tying everything together. So the network on chip provides a dedicated resource, not programmable routing per se. It's a dedicated network for communicating between these major subblocks. And then you've got DSP functionality. So this could be a DSP slice, which has been enhanced. It used to be the DSP 48s. In this technology, it's the DSP 58s. So not only is the multiplier wider, but there are different modes of operation, including being able to do 3 separate 8-bit operations in a single slice. So it's a lot of additional capabilities you have there. So these are things that are common to all of the different families. Now, as far as the families themselves go, so you've got the Prime, you have the Core, and then you have the Premium. So the Prime is really intended to be the foundational and probably the mid-range. This does not have the AI engines, but it will have the FPGA fabric. You've got the processing cores. You have the platform management controller, which is going to play a really big part of what we're doing. You've got the network on chip, and then you've got the DSP engines. Now, the DSP engines are technically still part of the FPGA fabric. So they're shown here separately just to highlight the fact that they do exist, but they are integrated within the overall adaptable engine. The interfaces here will run up to 32 gigabit seconds. So this will be your kind of baseline transceiver up to 58 gigabits. You've got multi-rate Ethernet, you've got MIPI interfaces built in. So for ADAS deployment, you don't have to recreate that. You've got general purpose IO, you've got the PCIe and the cache coherent interconnect capabilities. So this is where you get the hardened PCIe blocks. And you've got support for both DDR4 and low power DDR4. And we can see that this would address a lot of typical applications that need high performance, manage the power dissipation, and higher levels of integration. So this is using, again, up to 58 gigabit transceivers, low latency, wide range of DSP operations. So anything that you've traditionally done with FPGA fabric and the MPSoC or even GPU solutions, you could do it here, and it should work faster and at lower power dissipation, overall lower cost. And you've got the upgraded memory and transceiver capabilities. The Core series, this takes pretty much everything that we've been talking about, but also adds to it the AI engines. Now, the AI engines are really unique. In fact, the first couple of training classes that Xilinx released all dealt with the AI engines. Now, it wasn't because necessarily we just wanted to highlight those. It was because if you look at everything else that's happening here, you could argue that, okay, I've done processing with an ARM-based processor. I mean, I've done applications, I've done programming. I've used traditional FPGA fabric, so I know I can code things in VHDL Verilog, or I can use a tool like HLS to do high-level synthesis, and I can take C code and translate that into IP functions. I can use the DSP engines, which are part of this, and I know how to either use the libraries that Xilinx provides or write VHDL Verilog code that will map to the DSPs. But I don't know how to use this. There's no way I know how to use this because it's never existed. So the first couple of training classes dealt with introducing the AI engines, understanding intrinsics, understanding the vector data types, understanding the SIMD pipeline, understanding how to ultimately fine-tune these. This even represents a different clock rate, because typically for this programmable logic, you're looking at clock rates of 300, 500 megahertz. But for the AI engines, we're talking about a minimum 1 gigahertz. So you take that and you combine it with the SIMD data paths, and you're talking about an incredibly fast, low latency, high bandwidth processing engine. But again, it's all proprietary. So you have to understand the architecture, you have to understand the instruction set, how to simulate, and then ultimately how to optimize. So the core series adds this AI engine on top of everything else. And this is going to allow you to do some things that, quite frankly, you cannot do elsewhere. If you look across the industry today, there's really no way to kind of replicate what's possible with the AI engines. And this is still part of the larger chip. So you're able to use this in addition to the adaptable engine. And in fact, we can have hardware kernels that go back and forth between. So I can have kernels that talk from the AI engine to functionality here, and from functionality here back to AI engines. I'm also using these core processors to control this. And when I say control, that really varies depending on your application. So you kind of have two different extremes. So let's start on one extreme. Let's say if I want this to just operate on its own. So once I power up, once I initialize it, I want it to just run and keep running. I can do that. Or I want the processor to be involved with every invocation of this. Now, obviously, this is slowing down my overall performance quite a bit, but I may need that level of control and interaction. So if I do that, then I'm using a feature that's called runtime parameters. So that means that the AI engine now waits on the processor before invoking. So you can do it either way. There's a tremendous amount of overall flexibility in how we design, how the blocks communicate, how much control is being exercised from the processor to the programmable logic, to the kernels, to the AI engine. So it just creates endless scenarios that you can exploit. The premium series, well, what does premium mean? Yeah, fastest data rates, fastest parse. And this is building upon the prime series, but here you've got the 112 gigabit transceivers. It's using PAM, pulse width amplitude modulation, and the other capabilities. Now, it does not have the AI engines. So once again, you look at your application, you look across these different families, and then you can decide what matches your performance requirements. One of the things that you may be attracted to this for is having like the high bandwidth memory, which is banks and banks of DDR4 that's built into the same package. So here's a quick overview, just a bit of a snapshot that looks across the core series, the prime series, and the premium series, and we see the